This is the robot eye's anatomy, and the diagram is not a sketch, it is drawn with the real parameters. The whole eye has 4 parts, a white field circle, a black pupil circle, a small highlight circle at the upper left, and an elliptical eyelid that only appears when blinking. There are no image assets at all. All the geometry comes from 6 constants, the center at 125, 61, the middle of the screen, field radius 62, pupil 32, glint 9, gaze bounds 26 and 14, and the eyelid half opening called aperture. Every slide from here on is just combinations of these numbers. First, the foundation is a pixel inside a circle. The textbook says distance less than or equal to radius, but distance needs a square root. The key observation, both sides are non-negative, so squaring preserves the order, dx squared plus dy squared compared to r squared, and the root vanishes entirely. A pixel can fall inside several circles at once. Who wins? Early returns encode the priority, outside the eyeball, black, under the lid, handle the contour, then glint white, pupil black, and everything else is the white field. Equivalent to the Linux painter's algorithm, but each pixel computes only what it needs. The pupil's center is not fixed, it carries the gaze offset gx, gy, confined to a radius 26 circle. And 26 plus 32 is 58, less than the field radius 62, this invariant guarantees at least 4 pixels of white rim no matter where the pupil looks. It can never crash through the socket. The glint center is glued to the pupil at a fixed offset of -11, -11. As the eye moves, the highlight follows the pupil but always keeps its upper left bearing, because in reality the light source does not rotate with the eyeball. This tiny detail is what makes the eye look alive. Now the blink. The eyelid is not painting the screen black, it is an elliptical opening, horizontal semi-axis fixed at 62, vertical semi-axis equal to the aperture. Fully open, the aperture is 62 and the opening is a circle coinciding with the field, shrink it and the opening squashes into a lens shape. Here is the core derivation. The Linux version calls sqrtf once per column for the opening height. Square both sides of the inequality, then multiply through by r squared, 3 steps of pure algebra give, a dy times r squared, is at most ap squared times r squared minus f dx squared. Only integer multiplies and a compare remain. Squaring inflates the numbers, so overflow must be checked. The worst case on both sides is 62 to the 4th power, about 14.8 million, the int32 limit is 2.1 billion. That is 145 times of headroom, safe by 2 orders of magnitude. The lid edge carries a 3-pixel white contour line so the black pupil never merges into the black lid. The implementation reuses the same formula, shift ADY by 3 and test again. Pixels that fail the original test but pass the shifted one form exactly that band hugging the opening, painted white. The blink animation is literally 2 frames, aperture drops from 62 to 26, then back. Why 26? It never fully covers the pupil, a full close and open would flip a huge area between black and white, heavy ghosting det in partial mode. The half blink looks right and costs little. Gaze movement uses a constant speed glide, a fixed 14 pixels per frame, not a fraction of the remaining distance, proportional steps decay like a spring, not like a gaze. The distance comes from an integer square root, and the step adds d over 2 for rounding, so small components never truncate to 0 and stall. Random gaze targets must be uniform inside a disk, done with rejection sampling, draw uniformly in the rectangle, retry if outside the circle. Simpler than the polar method, which needs square roots and trigonometry, and unbiased. The generator is a 1-line LCG, seeded with micros as entropy each round. Finally, memory. The Linux version needs 34.5 kilobytes of framebuffer, this chip has 2. The solution, the image is a function. I_pixel is pure, its state is just 3 integers, gx, gy and aperture, and every byte is computed at the moment it streams out over SPI. One inherent limit: this RISC-V core has no hardware multiply instruction. Each multiply runs a roughly 100-cycle software loop. With around 100,000 multiplies per frame, rendering takes about 0.3 seconds, plus the refresh, roughly 1.5 to 2 frames per second. For an eye, exactly right. To sum up the port, 34.5 kilobytes of framebuffer became 3 integers, floating point square roots became squared compares, and 200 lines of integer geometry replaced the whole rendering pipeline, and by the user's own hardware test, the MCU version looks better than the reference platform. Get the math right, and 16 kilobytes wins.